All right. Lesson 3 in Unit 2 deals with velocity and rates of change and things of that nature. Practical applications of the work we're doing in the calculus. So again, calculus deals with rates of change, things like velocity and acceleration. So we'll do as much application as we possibly can and see where that leads. Things we should talk about. We should talk about motion along a line, because these are the applications they love the most. And by they, I mean the College Board. This is the stuff that pops up all the time. Usually there's some sort of displacement function, and that displacement function is called S. S usually represents displacement. I'm not really sure why. And it's some function of time. No idea what function of time, but it's some function of time. Things we should know about. Again, when we talk about average velocity is your displacement at t plus delta t minus your displacement at t over delta t. And again, this is nothing more than a change in displacement over a change in time. Average velocity, that's what it looks like. When we talk about instantaneous velocity is the derivative of displacement with respect to time. It is f prime of t. So when you see instantaneous, that always, always, always means we're taking a derivative of somebody. The other thing to bear in mind is acceleration. Acceleration is the rate at which the velocity is changing. So we abbreviated A for acceleration. It is the derivative of velocity with respect to time. So it's the second derivative of position with respect to time. So if I have a displacement function and I've got to get to acceleration, that's two derivatives. One to get me velocity, one to get me acceleration. If you're interested, if we look at how acceleration is changing, acceleration change is called jerk. And the reason that makes sense, well, you're riding in a roller coaster or whatever, and it jerks really hard from one side to the other because the acceleration changes sharply. So the acceleration's derivative, the second derivative of velocity with respect to time, the third derivative of position with respect to time is called jerk. It's never going to show up on an AP exam unless they define it for you in the context of the problem. I will bring in one other quick side note coming off of velocity. Speed is different than velocity. Speed is the absolute value of velocity. Speed is the absolute value of velocity. It is the absolute value of the derivative of displacement with respect to time. Speed is always positive. Whether velocity is positive or not, speed is always positive. So these are things we've got to have in our toolbox. This is one of those things, you've got to put it on a flashcard, you got to make sure it exists somewhere in your brain. So let's shoot a rock. A rock shoots upward with height S equals 25t minus 5t squared meters at t seconds. By the way, so we're all clear, this 25 represents the initial velocity in meters per second of the rock. You can make up your own problems. Within the sphere of Earth's gravitational influence, you can make up your own problems by saying, okay, I want the initial velocity to be whatever, and that goes in that slot. That'll do just fine. I want to find things like the maximum height of the rock. I want to find the velocity and speed when the rock is 30 meters off the ground, which we assume is flat and has height 0. And I want to make sure I can find the acceleration function as a function of time. So the maximum height, what happens to this rock? This rock goes up and comes down. That's what it does. It goes up and it comes down. At this point at the tippy top, that's the maximum height. At that maximum height, the slope of the tangent is 0. So at the maximum height, velocity is 0. And I know what velocity is. It's the derivative of displacement. So that's 25 minus 2 comes down, multiplies by 5, 10t. And so I know at what time this happens. It happens at 2.5 seconds. But that's not what I'm asked. I'm asked what the maximum height is, and so I've got to sub that 2.5 into the displacement function, and that gives me, 25 times 2.5 is 62.5. 2.5 squared is 6.25 times 5 is 31.25. So that's 31.25 meters. That's the maximum height of the rock off the ground. Then, looking for velocity and speed when the rock is 30 meters off the ground. Well, when the rock is 30 meters off the ground, the rock is 30 meters off the ground. And you can solve that quadratic equation and figure out that t is 2 or 3 when that happens. That almost makes sense. If this is happening at 2.5, then on either side of that, equally spaced, has to be the places when the rock is 30 meters off the ground. So velocity at 2 is 25 minus 10 times 2 is 20. That's 5 meters per second. So the speed is 5 meters per second. Velocity at 3, now that's 25 minus 10 times 3. So that's negative 5 meters per second. But the speed is still 5 meters per second. And this almost makes sense. The slopes of the tangents on either side are equal but with opposite sign. That makes sense under the great physical principle that what goes up must come down. Looking for acceleration. When we're looking for acceleration, we're looking for the derivative of velocity. The derivative of velocity with respect to time. And we're going to write down that a is dv dt or v prime of t because we want the grader to know that we knew to take the derivative of velocity. We want the grader to know that we knew what to do. And so the derivative of velocity, derivative of that's the derivative of this thing. And so the derivative of 25 is 0, but the derivative of negative 10t is negative 10. And the units on that are meters per second per second. Meters per second per second. So there's your acceleration function. Excellent. Let me go one more. Okay, one more example as an application out of economics, the idea of marginal cost. And so what I'll do is I'll set this up. Let's let c of x equals 0.0005 x cubed minus 0.38 x squared plus 120x. This is the cost of a flight with x passengers. Obviously, the number of passengers affects how much it costs to get that plane in the air. And so I want to look at the marginal cost of adding a passenger if the number of passengers is 150. Now, what we mean by that, economically speaking, we mean that the marginal cost is the cost of getting one more person on that flight, of increasing from 150 to 151. So I mean the actual marginal cost, I'll just skip ahead, the actual marginal cost, the actual cost of the 151st passenger is just whatever your cost is at one. I should use green, shouldn't I? Because money is green. The actual cost of that 151st passenger minus the cost of bringing in 150. So that happens to be, and this is a quick calculation, $39.60. You can sub in 151, sub in 150, and subtract. In calculus language, the marginal cost is the derivative of the cost function at 150. Marginal cost, and again, on an AP exam, they would have to define that for you. They would have to say, given a cost function, the marginal cost is the derivative at that value. But I'm just saying what that is the cost of bringing on a 151st passenger. So I know what C prime of x is. C prime of x is the derivative of that thing up top. So that's 0.0015x squared minus 2 comes down, multiplies by the 0.38, 0.76x plus 120. And if we sub in 150 to that derivative function, we get $39.75, which is pretty darn close to the actual computation of C of 151 minus C of 150. But the derivative computation is much easier, and so economists look at that as an easy way to look at marginal cost. So just so we're clear that not all of the applications of the calculus are physical or physics in nature. There are applications in economics and in other places. What do you need to know? You need to know this slide. You've got to know those things cold, because those are the applications that are going to pop up that they do not have to explain to you. They are under no obligation to tell you what acceleration is. If they're going to bring in a problem on marginal cost or some of the other more exotic applications of the derivative, they have to tell you that. Okay, so there you have it. That's a quickie lesson. When we come back tomorrow in class time, we'll do some more Pete the Particle type problems, because those are the kinds of things we should walk through together. And I will see you then. Thanks, everybody.